Okay, good. So today we will try to understand how to do antenna modeling using EZNEC. So EZNEC, actually NEC, so it is numerical electromagnetic code. It's an antenna modeling code that was developed long back in the Livermore lab, which is part of UC Berkeley. Now it is open source. So one of the hams, if I remember correctly, his name is Ray Levallen. I think it is W7EL. So he created EZNEC. Some people pronounce this as EZNEC. Some pronounce this as EZNEC, EZNEC. I like to pronounce it EZNEC. You can pronounce however you want. Okay, before we start, just want to set the expectation here. So this is an introduction to EZNEC. My interest in exploring this, in playing with this software, is or was purely academic. I wanted to understand various antennas, antenna propagation patterns. That's it. I am not a home brewer. The probability of me making an antenna after modeling using EZNEC is tending towards 0. So whatever I have learned, I will share it here. If you have any questions, and if I know the answer, I will answer. If I don't have the answer, I will say I don't have the answer, but I will get back to you after doing some research. So the expectation that I would like to set, so you all get familiar with this software, you all get familiar with the basics of antenna propagation, and then some of you or many of you will go ahead and do some actual antennas. So that would be good. Using this software, modeling some interesting antennas and making it, that would be good. Okay, so yes, I will make it full screen. So my voice is okay for you. My screen is visible to you. Actually, you know, most of the amateur radio software that you find, they're not very user-friendly, in my opinion. And this particular software, EZNEC, is the same. What I am using is a demo version. It's not a paid version. I just went to the EZNEC website and downloaded it some time back. This has certain limitations. Some of the limitations that I have come across, I will explain it. One of the limitation is it opens up to many screens, and I'm not able to make some of the screens full screen. This is the opening page. This also, unfortunately, I'm not able to make full screen. Let me try if I can somehow make it. No, it doesn't allow me to make it full screen. If I share the app window, again, there are some issues with the software or maybe with the 3CX. If I share the app window, I did, along with Srikumar, we did a dry run. When I share just the app window, it is not rendering properly. And this is going to bring up too many screens as we walk through step by step. This is going to bring up too many screens. So that's another problem. If I share just the app, if it opens some other screens, it won't be visible to you. Okay, good enough. So I'll try minimizing the browser so this is more visible to you. In case I won't be able to see what is happening. Okay. This is better. Is the screen more visible to you now? Okay, good enough. So now let's start. Time is 7:41. I'll keep an eye on the clock. So I can go on for a couple of hours, but my intention is to finish it in say 45 minutes, and maybe we can discuss a little bit after that. All right, so this is the starting window. This itself is a little complicated. That's the reason I'm saying UX is not that great for many of this free software. Okay, can you see my cursor? Fine. So this particular area, menu at the top, this is mainly to set up your preferences. For example, when you say ground, there are so many parameters for a ground. You can set it up here. So those are a little bit advanced, so we will not get into that. Let's look at an introduction now, and after that you can play and get into the complicated stuff a little later. So this window inside, all these items with an arrow on this side, those are your inputs. And all this is all the button outside, this is your output. Okay, so let's start with a simple antenna, a dipole. So currently this is set for 7 megahertz. I'm going to make it 14 megahertz. So you just click on the frequency, it opens up a small window, you enter the frequency in megahertz, 14 megahertz. Hope that window is visible to you. I'm going to click OK. So don't worry about these warnings right now, because as we make it complete, these will disappear. And these are all warnings, and you can ignore it right now. So I have enabled warning set to yes. So that's the reason they pop up. So as we gave the frequency, it came up with the wavelength, 21.4138. And by the way, it's all in meters. You can go here at the units and say whether you want meters, millimeters, feet, inches, wavelength, whatever you want. I like metric system, so let's go with meters, and I hope you all are more familiar with the metric system than any other system. So 21.4138. I'm going to open up calculator. Let's take half of that. $10.7069. So let's start the first step, or maybe the second step. Now this is a wire antenna, so we have to give the dimensions of the wire. So click on the wires arrow. Now it is full screen. Some screens are full screen, some are not. So what was the, so here you can enter all the wire elements of your antenna. And by the way, every antenna you can break down to wires. So think about any antenna. Those will be broken down to wires, including say a Yagi antenna. Even all the reflector, the reactors, all those can be modeled as wires. So here it's a dipole. In this software, dipole is considered a single wire. You're going to feed at the center of it, but dipole is a single wire. We'll come to that. When we feed the wire, we'll come to that. So now you come to a three-dimensional space where you have to give the coordinates. So I'm going to say the convention in the software is Z or Z is always the ground. Z equals 0 is the ground. So I am going to say my coordinates for this antenna, X 0, Y 0, Z, I'm going to say I'm going to put this antenna 10 meters above the ground. If I make it 0, that is ground. I don't want this in the ground. There are certain cases where you want to start the modeling with the ground that we will touch upon when we come to maybe an NFET. If you have the time for an NFET, we'll come to that. So I'm going to put it at 10 meters. Now, what was our length? 10.7069. So I'm going to spread my antenna on the x-axis. 10.069. Y-axis again 0. Z again 10 meter above the ground. And I'm going to use American wire gauge AW12. So you can give the wire gauge as #1214, and if you want to give the diameters in millimeter, you can do that as well without the hash. Now segments, this is an important thing. See, the antenna and the software analyzes every wire at a segment level. A segment is the basic unit of an antenna in the software. The vibration of the segment, or the electromagnetic vibrations in a segment, that is what is being modeled by the software. So the more number of segments, the more clarity you will get. With this demo software, the maximum segments you can have is about 20. So I'm going to go with 11. Why 11? I'll come to that a little later. So when we feed the antenna, I'll tell you why I chose 11. So that's it. Now there are a lot of other options. If you want to create, let's say, a Yagi, then you can add more lines to this. You want to create like a zigzag end fed. You can add more here. We'll come to that a little later. So right now, for the simplest antenna, for the dipole antenna, 10 meters above the ground on the x-axis, 14 megahertz. We have entered the wire details. Now we can close it. Now, what is needed next? We need to feed it, right? So that is where the source is. Again, I'm going to assume for simplicity that we are going to feed without any transmission line. So our transceiver is directly connected to the antenna. That's an assumption I'm taking. So I'm going to say there can be multiple sources. Let me make it big. So in this case, simple source, only one source in this antenna system. So it is, I'm going to feed it. In the last step, we created a wire. So in wire 1, I'm going to put it at the center. So 50% from the end. This means from the end. I'm going to say 50% from the end, and it automatically calculates which segment. So this is where the segment is important. So we chose 11 in the last 11 segments in the last step. Why? We want to feed at the center, so it automatically calculated segment 6. If we had done, say, 10 segments for it, it would have taken somewhere in between, and maybe some confusion for the software. So I have chosen 11, and number 6 is where we are going to feed. And 1 volt. By the way, this is the source amplitude. I'm going to feed 1 volt for the dipole. Since it's a single source, the phase doesn't matter. It's always 0. So if you have multiple sources, you can say one source you feed it at 0 degree, and the second source you feed it at, say, 30 degree off. So those complex antennas can be done. And this, you have multiple options here. I'm going to select a voltage source. You have a current source, which is an I. You can also feed split current, split voltage. These two are required when your antenna wire is not uniform. For example, if you're doing an inverted V, you have to have a split voltage or split current. So for simplicity, I'm going to take a voltage source, and we are done with that. Now, briefly, if you want to add inductive or capacitive loads, you can do that. If you want to shorten, you don't have much space, you want to shorten the wire length, but you want to increase the electrical length, you can load it with inductive load. And if you have, when you look at the impedance, if you think at the resonant frequency, you have reactive, either inductive or capacitive load. If you want to null it, you can give the opposite. If you have an inductance at the resonant frequency, give it a capacitance, and vice versa. So this is where you can do that modeling. I'm not going to touch that right now. transmission line as explained earlier. Let's assume that we are directly putting our transceiver at the antenna. So I'm not going to use a transmission line. Transformer, NFED, you want to do impedance matching using a transformer, you can do that. You want to do voltage ratios at the source to the feed, you can do that. I'm not going to do that right now. And if you want to have L networks for more impedance matching, you can do that. You will not do that. Again, ground type here, you can select your ground type. In this case, let's look at what are the ground types. So loads, transmission lines, transformers, L networks, slightly advanced. Let's get into that if we have enough time. Now let's look at ground type. So this software provides multiple ground options, free space. How many of you live in free space? I don't. So this is just theoretical calculation. So typically, I mean, we can go for a real high accuracy, or mini-NEC is an advanced modeling standard, or a software, or a code. It provides a lot of ground options. We can use that. In this case, let's go with high accuracy. It's a real ground, high accuracy. We'll come to more details on that on the ground. Okay, so we selected that ground. So then it selected certain things automatically for us. So let's understand what is the description of that ground. Okay, so when we say a ground, so when we started, we mentioned about settings. These are the settings already done there. So for a ground, these are the options you have. So I'm not going into the details of that. So we selected average. Let's go with it. Now, let's go with the copper wire. You can play with different things. You can even go with the user defined. Let's not do that now. Unit we already selected. Plot type. Let's start with the 3D and then we'll slice and dice all that. Step size. This is going to be angular. The plots are going to be using angular measurement. So this is 5 degrees every step. Now, how are we going to compare the performance of our antenna? I would like to compare it with dBi. So what is dBi? First of all, we all know dB is a comparative scale. dB always says with respect to something, this is what it is. If you remember the formula, it is 10 log V1 by V2 or P1 by P2, I1 by I2, all that. 3, when we say 3 dB high, that means double the power or double the voltage or double the current with respect to whatever is our base. Okay, in this case, I'm going to, the antenna provides, or the EZNEC provides comparison with isotropic. What is an isotropic antenna? It's a fictitious antenna which radiates uniformly in all directions. It doesn't exist. It's a theoretical antenna. So a standard dipole, I believe it is 2.15 dBi. I may be wrong. So let's compare with dBi. So if you want to compare with DBD, maybe advanced options, paid versions of the software may allow you to do that, or you just subtract the gain by 2.15. Since it's a comparison and logarithmic, you can add, subtract, all that. So comparison here is with respect to dBi. Now, by default, the software does 50 ohm systems. The feed line is assumed, the antenna impedance is assumed to be 50 ohms. If you want to get another level of comparison, you can do that. So I'm going to go with 75 ohms just for my comparison. That is pretty much we need as the input. So there are certain other things when you view the 2D and 3D. There are some settings that you can do, near field settings, far field settings. We will not get into that now. Okay, so we have done our basic setup for a dipole. Now, I just want to run through this very briefly. We first gave the frequency in megahertz. It gave us the wavelength. We are modeling a half-wave dipole. We took half of that. We created one wire with 11 segments. We added one source at the middle of the wire, and this wire we modeled in 3 dimensions: X, Y, and Z or Z. So the Z axis is always the vertical axis in this software. So 0, 0, 0, XYZ coordinate 0, 0, 0 is the ground. So we have put 10 meters above the ground. One source, no loading, no transmission lines, no transformer, no L networks, real high accuracy ground, copper wire, all units in meters. You can plot in 3D. Comparison is with isotropic antenna. Alternatively, we will compare it with a 75 ohm system as well. Now, this is the output. You can open new files, save it. You can enter antenna nodes. Already saved something, so I'm going to leave it there. Now, before I get into current, source data, load data, far field, near field, let's get into SWR. Or let's see our antenna first. So this is the 3-dimensional view of the antenna. So I just want to check how are we progressing. Is it too fast, too slow? My audio is clear to you. My desktop is clear to you. Okay, all good. All right. So this is the UX issue I'm talking about. There will be too many screens when you do this. I have a tendency to make the desktop very simple, so I have closed most of the other, source, wires, and all those I have closed it. So I just have to. Okay, so this is the antenna that we have modeled. This is the ground. X is 0, Y is 0, Z is 0. 10 meters above the ground, we have the dipole on X-axis. Remember that. Please remember that the antenna is on X-axis. So when we look at the plots, this will help us a lot. And 11 segments we are feeding in the middle. Now on this side, this is a simple antenna. You don't need to slice and dice. If you have a complex antenna, if you are 3-dimensionally inclined, you can do a lot of juggling. So this is the antenna. Now let's look at the plot. All right, so this is where it's getting interesting. So this is the 3-dimensional plot. I'm going to explain 2 more things here. One is the elevation plot. The second is the azimuth plot. So what is an elevation? Elevation is, I think, we all use in day-to-day. So if I am talking to Sri Kumar, the way I see Sri Kumar is the elevation. When we stand in front of a house and we look at the house, that is the elevation. What is an azimuth? It's a bird's eye view. If you have a drone or you can fly and be a bird, you fly over a house and look down. That is the azimuth. So I hope the analogy is helpful to those who are new to this antenna plotting. So the experts here, day-to-day thing, so no problem. Now here you can actually turn it and understand a little bit more. So I said, see, remember our antenna is on the X-axis. Now let's see. Let's make the X-axis straight to us. So in 3 dimension, this is the elevation. Z axis is vertical. This is the X-axis. Y-axis is perpendicular to us. This is the elevation of this antenna. elevation of antenna, again we need to classify that. So the elevation, you can go around this antenna. It's a circle. Assume there is a circle around it. Go around and you will see different elevations. So this elevation is where x-axis is in parallel to the screen, and we call it azimuth 0. In this software, we call it azimuth 0. So if you go to many other software, usually the angle start from the north. The top is your north, that is labeled as 0, and then some software I have seen clockwise, counting 10 degree, 20 degree, 30 degree, and some software anti-clockwise. Let's go with the convention used here. The x-axis is always, and positive x-axis always starts with 0, azimuth 0. So we come to, when we take the slice, you'll understand it more. So this is the elevation at azimuth 0. Now let's rotate it again. So now we saw the elevation in 3 dimensions. Now I'm going to rotate it again. So I'm going to make this z-axis pointing towards us. That is azimuth. That's the azimuth plane. Okay. This is the azimuth plot. So the inference from here, the antenna is on the x-axis. It is a simple dipole. So it is radiating. The major lobes are towards the sides. Okay. Now let's put it back. And again, you can rotate it very many ways and get a feel of how the antenna pattern in 3 dimensions is. Okay. So let me stop here. Now let's go to the 2 dimension. All right. So this is the elevation plot. Look at it. This is the elevation plot. And I have selected the elevation slice. I'm going to go to 0. This is elevation plot at azimuth 0. And we can change it. So those who are not familiar with 3-dimensional modeling may need to spend a little bit time if you would like to get into the details of it. So you can, in the elevation plot, or the elevation plot can be taken at different azimuth angles. So let me move it and you will see the difference. So at 60, you have another radiation pattern. As we move forward in angle, radiation pattern of the antenna that we just modeled will change. Right. So I went back to the 0 azimuth. Now let's try to understand some of these numbers. So this is an elevation plot at an azimuth angle of 0 degree in the 3D. So forget this for a moment. This is one of the drawbacks of this demo version. The numbers don't have much clarity, but let's ignore this. Let's jump into this box. 3D max gain. What is the maximum gain of this antenna that we just modeled? It is 7.01 dBi. Remember, it's a dipole. In the dipole, the maximum gain we are getting is 7.01. Standard dipole gain is 2.15. But in our antenna, based on the modeling data that we have in the demo software, we have got 7.01 dBi. So since my intention is purely academic, I want to understand, and I'm not going to improve this antenna. I never bothered to get into the details of this calculation. If anybody is interested in home brewing based on this modeling, I can dig deep and get more details on why 7.01 dBi for this dipole. Is 2.15 dBi that we talk generally, is that an average? All that I can dig deep, look at the calculations. For time being, I'm happy with it. Yeah, this antenna has got 7.01 dBi. I'm happy with it. Now we have taken a slice, right? We have taken a slice at the azimuth 0. For this slice, what is the maximum gain? At an angle 50. So this is the maximum gain for this slice. Elevation angle 50. So this side will give you the cursor information. So the cursor, this green dot, is sitting at 50 degree, and this is the gain stats there. The maximum gain here is 0.4. I'm going to ignore these two things for the time being. These are all comparison with the maximum we have. Now there are two more concepts. Beam width. What is a beam width? Typically, we understood 3 dB is double the power. So minus 3 dB, the difference. So when from here, when we go, this is the maximum signal strength or the radiation power strength. As we move here, it is coming down. At some point, it will be 3 dB down. We mark there. On the other side also, when we move minus 3 dB down, we mark it. This is the beam width of this lobe. It's called minus 3 dB beam width. So 3 dB, as you know, minus 3 dB means half the power. Plus 3 dB means double the power. Okay. So the angle between half the power points of a lobe is the beam width. Now, side lobe. Now we have one lobe here, we have another lobe here. So let's call it primary lobe, let's call it secondary lobe. So what is the gain of this lobe? Again, symmetric, right? Again, 0.04 dBi at an elevation angle of 130 degree from here. So we start with here, count this way, counterclockwise to 130. What is the front and side lobe ratio? It is the same. So it's the same. It is 0. It's a logarithmic scale. So it is 0. So you may think it is 1, right? So the ratio of power is 1. When you apply log to that, log of 1 is what? 0. Now, as we change this azimuth angle, you can see the gain changes. Okay, so I will, to the time constraints, I will stop here with the elevation plane, elevation slice. And also keep in mind, I wanted to point out one more thing. See, the maximum is at what angle? 50 degree. So low elevation radiation is not much. I'm not saying there is none, but the power is much less. This antenna, this dipole antenna is very good in radiating at 50 degree for in this slice, in this 0 degree azimuth. That is what I see. Now, if I go to the perpendicular 90 degree, 90 degree, this is much better, right? So this is perpendicular to the axis of the antenna. Our antenna is on the x-axis. So if you look at y-axis, it is radiating much better. So even in that case, the maximum is at 30 degree. So dipole antenna, if you're looking at low angle, low elevation angle propagation, maybe dipole is not what you need. you need to model a vertical antenna and look at it. Dipole still radiates in a low elevation angle, but most of the radiation, maximum power, is at higher angles. Okay, fine. Let's look at the azimuth slice as well. So here itself we can switch. And once you switch, this cursor is azimuth cursor. Angle you need to move is the elevation angle. This may be those who are not haven't spent much time reading antenna radiation pattern or looking at slicing three-dimensional pictures. It may be slightly difficult, but it is very easy once you spend some time. See, I am slicing. I'm taking azimuth at different elevation angles. Just think about an orange. You can cut the orange. You keep the orange on the table 1 centimeter from the table. You can cut the orange. The cut will give you a smaller circle, 2 centimeters bigger circle, 3 centimeters bigger circle, until you reach the middle of the orange. It will grow, and after that, the circle of the slice will reduce. This is exactly what the azimuth plot is. So as we change the elevation angle, so at the lowest zero elevation, there is not much happening. So as we increase the elevation angle, the field is increasing. At some point, it hit the maximum, say at 35, 30 hit the maximum, and then it is coming back. So this is how you read the elevation and the azimuth. I am going to close it for the time being. So the three-dimensional pattern, you can rotate it whichever way you want. So let me keep the x-axis visible. So this is the three-dimensional pattern. Just want to recap. So time is 8:15. I said 1 hour, so maybe we have another 15 minutes. I'll try to cover maximum possible within that 15 to 20 minutes. So what we looked at, so we entered all our information. We then looked at antenna in 3 dimension. We looked at the frequency plot in 3 dimension. After that, we did the elevation slice. We did the azimuth slice. Now, let's look at a couple of other things here. You want to know the SWR, right? Let's click here. This antenna is modeled for 14 megahertz. So let's look at the SWR from what? 12, 16 megahertz. 12 to 16. And what should be the step? We'll take one. Let's say how it runs. It takes some time. So we're going to sweep the antenna from 12 megahertz all the way to 16. So we model this for 14. So let's see how the SWR is going to be. MJK0541. Can you tell once again the step to get the 2D plot for the radiation? Okay. Keep it open here. So in the frequency of so this is the part. So this is the far field plot. Click on it. It comes in 3 dimension. Do you see this? Select this to make it 2D. And then in 2D, you can either select the elevation slice or the azimuth. You can also turn it off, come back to 3. Hope it is clear. There is one more option. See, in the input, what is it? Here we said we want to see 3D. can select azimuth or elevation. Simple as that. I typically, I mean, while experimenting with this, I want to see 3D and then take slices of that. So SWR, center it again. So from 12 megahertz to 16 with a 0.1 megahertz step. Let's sweep it. Right, this is our SWR. So by the way, we are doing this analysis for 50 ohms. Remember, in one of the steps, we also selected, we want to see the 75 ohms system as well. Look at 50 ohms. So we have 15.7 megahertz. We have 1.52. That's the lowest. Yeah, 14 we have 2. And what might be the reason? Let's look at it. You see here the impedance of the antenna at that particular frequency. 1.52 is good enough. By the way, my theoretical take on the SWR. SWR is not a big deal. As long as it is not infinity. As long as it is in single digits, it's not a big deal. That's my theoretical take on it. So I'm sure many of the experts here disagree with that. But I have a theoretical take on it. I'm sure many of you have a lot of practical experience on proving and all that. So we can have a different discussion on that later. So 1.52 is good enough. If you look at the commercial tuners available, even if you have 3 or 5, I think it is good. Those can be, but it's a dipole. We shouldn't be using a tuner. Without a tuner, it should be resonating. So let's look at why this particular antenna is not 1:1. Multiple things. One is this is a modeling software. This is not a practical antenna. This is a model antenna, and this is based on NEC, which was developed long back in a university lab somewhere in UC, which became open source. So there are a lot of modifications to that. Those modifications may not be open source. In an advanced commercial software, if you want to do commercial modeling, this kind of simple antenna may have 1:1. So this is free, and we are just experimenting. At least I am learning more about antennas, antenna propagation. Long back, I learned when I did my BTech in electronics, but that was just to pass the examination to get the degree. So this time around, I really wanted to understand how this happens. So that is what I'm doing. So 1.52 is good enough. Look at the impedance. So at 1.52, the impedance of the antenna is 75.8. That's the resistive part. The reactive part is 1 point, which is okay, which is very low. So this is the problem. I think this is the problem. So we are matching it with a 50 ohm. So let's shift it to 75. So the antenna shows 75. The impedance of the antenna is more resistive here, around 75 ohms. I'm going to switch to 75. Now you can see it's 1.017. It's almost perfect. Cannot complain. So there are limitations for this demo software. The models used within this, but at least even though we tried to model it for 50 ohm, we're getting 1.52, 14 megahertz. We didn't exactly hit 14 megahertz, 1.5, 13.7 is happening. And if you switch it to 75, if you're okay to feed it with a 75 ohm system, maybe a ladder line or something. So this works out better. Now, the next thing, so the impedance is way off. There are ways to adjust it. That is what I want. Okay, so I'm not going to get into the other parameters here. So we understood SWR plot, how to get it. Again, 50 ohms versus 75. How to read SWR, how to read the impedance of the antenna. So all good as an introduction. I'm going to close it. Now, so you saw the impedance there. So our antenna is more of resistive, which is good. A very low portion of reactive. So if you have more reactive, then you can do a lot of things by playing with the matching networks. I'm not going to get into that now. You can also do transformer. If you have an infrared, you can do transformers. All that. So, for the time being, considering the 1 hour we have, uh, okay, Sineosh. So the default is for 50 ohms. So here we also wanted to see 75 ohms. So since you asked that question, I'm going to put it back to 50. I don't want anything other than 50. So I'm going to recalibrate. I don't want to reuse it. Let's try to recalibrate. So this is 50. I'm going to go back to recalibrate everything. See, both are the same. So again, 13.7, 1.52. So the system by default does 50 ohms, and we have the option to add one more system. So we selected 75 here. See, alternative SWR is at 0 impedance. So we said 75. You want to see 75 as well. Okay. What else to cover now? It's 8:23. I will stop this presentation here, and maybe if there are questions, I'll try to answer those questions. And if we have more time, maybe we can look at maybe an infrared. Low angle radiation for a vertical. Okay. This comes with a lot of vertical antennas. So let's open up one of the items that came along with this demo. I want to save it. See that these are the experiments I have done. Let me find out a vertical from here. And in this you can look at very many complex antennas as well. Let me find out a vertical. Okay, here is one. Let's look at the antenna. Okay, it's very close to the ground. This is 7 megahertz. Let's look at the wires. It's actually starting with the ground. Okay, so this is, I'll briefly explain what this is. How can an antenna start with the ground? And it goes up vertically 10.3 meters. It doesn't use any wire gauge calculations. It does in millimeters. 10 seconds. Fine. Let's look at the source. There is only one source. It is fed at the end. Okay. So we said position this at 0. And the 0 or the beginning of the wire is actual ground 0, 0, 0. The system automatically push the source slightly above it. Now we will see the plots using different grounds. So this is a real high accuracy. Let's take a real. Okay, so when the wire is connected to the ground, we have to use the mini neck. Fine. Let's Let's look at the plot. Let's look at the 3D plot first. See the 3D plot you see, you can see close to the ground. Now let's take an elevation. See this, the maximum radiation between an azimuth angle, azimuth 0. So the maximum is 25 degree. The previous angle I think we saw at 30 degree. I'm going to change this slice. Okay, this is a, there is not much change. So this vertical antenna, the maximum is coming at 25 degree. So CPL, if you're interested, I can share something where I've done a vertical where I could see at 15 degree as well. It doesn't seem to be here somewhere. We can take it offline in the interest of time. So CPL, I think let's connect offline. I will share a vertical where the radiation is at low elevation angle is at low. Pre-install examples of ground plane. Yes, there are. I mean, please install the software. There are some pre-installed examples. You can see that. And I believe there is a ground plane. Yes, there is a ground plane. What was the origin of the radiation plot? Was it at the source speed, voltage speed, or origin is of the wire antenna float screen? Okay, so you saw the three-dimensional antenna, and after that we came to the three-dimensional plot. So it is always from the source. So for the dipole, it is from the center of the dipole. Can you please model an inverted B at 120 degree and see the SWR at 50 ohms? I can, I have some files, I'll share it with you. So if you have time, I don't think we have enough time to model an inverted B right now. So if you have some time, I want to show you an infrared antenna in a restricted space. So we have maybe another 10 minutes. So CPL and Synosh we can color. CPL, Synosh, we can connect later offline. Can you plot SWR of horizontal dipole 14 megahertz to megahertz? Then what parameters to adjust to make the entire band close to very low SWR 1:1? See, in this dipole we have done. We have tried it with the dipole is initially we looked at it 50 ohms system, then we looked at 75 ohms. So with 75 ohms, it came almost close to 1.1. Any other questions? If you are putting here itself. Okay, so time is the limitation. I would like to close it in another 5 minutes. So I will share that plot. So and again, it will be interesting. So I will share that file, vertical antenna file with Sri Kumar, and he can blast it to everyone. So you can install the software and open it up. So what a wonderful way to make everyone download the software and play it. Okay, so can I assume we don't have any more questions? So I just want to show you a transformer, and then if time permitting, I want to will raising the set position higher change. Yes, it will. So if you go to free space, it will change a lot. So that is something you may want to experiment. So let's open up our dipole. I hope I see it. Maybe I did. Okay, I didn't save it. Never mind. So look at the plot in free space. Okay. Now this is an elevation slice. You have on top of the x-axis, below the x-axis. Now I'm going to make it real ground. Now look at it. You don't see anything below the x, everything is above x. So as you change the ground, as you increase the height, it will change. Any other question or the last question? And after that, I'll show you an NFET, and I also want to show you how a transformer can be connected. Okay, so let's open up an NFET. So here is the antenna. So I'm going to run the antenna initially on the vertical axis, and then on the x-axis, then on the y-axis. Why? I have a 7.5 cent load, and most of that is my house. So if I want to put an NFET, I have to have some jugaad. I don't have a better way to explain it, so I'm using the word jugaad. Okay, so here there are 3 wires. You have seen it, one vertical, one on the x-axis, and then another one on the y-axis. And by the way, it starts with the ground. I have a source. It is a virtual source. So that is something you need to understand. I am using a transformer to match the impedance. So that transformer cannot be connected directly. A power supply cannot, sorry, the source cannot be connected to a transformer. A virtual, so we need to create a virtual source. So on the port 1 of the transformer, I'm putting my virtual source, and port 2, I'm connecting to the wire. I'm matching the impedance here, 50, and I'm converting that to 2500. Now, the source I'm putting on the virtual, and that virtual source or a virtual wire is connected to the transformer. Look at that plot. It's not bad. It's not perfect. It's not bad. Even if an NFET with this software, it is good enough. And I want to show the SWR as well. So I'm sweeping the entire range. This is what I have. Not the perfect system, but a reasonable system. And you can optimize it a lot. Look at the impedance. So there is capacitive reactance. So I can add more. I can load it. I can load it with reactance, inductance mainly, and try to negate this. So there are very many ways we can play with it. All right, Ellen, just want to show you the inverted. There is an inverted that comes by default. This is the backyard V. You see the antenna. So it uses 2 wires. So in the dipole, we just had 1 wire. For the inverted, we have to do 2 wires. And then see 2 power supplies. This is what I had mentioned. Split source had to be used. You cannot put a single source in the software onto the inverted V. It has to be split. So look at the wires. Coordinates, you can go in detail. This comes by default when you install the software. And if you look at the source, yes, it is put at the end of wire 1, and it's a split current source. You can also use a split voltage source. And you wanted to see the SWR, right? It's for 14 megahertz. So let's sweep from 12 to 16. 1. Okay. So we have 14.7. We have 1:1. And 75. 1:6. I'm not sure whether LN or CPL asked this question. CPL, I forgot. So if LN asked this question, CPL, your question was change this to vertical and show low angle radiation. Okay, so vertical we saw. I will share a low angle offline. I hope other than that, I've answered all the questions. So it is 8:38 on my clock. So we just did 1 hour something. So if you don't have any more questions, I'll close this presentation. Last 1 or 2 questions. All right. Thanks everyone for joining. And thank you, Srikumar, for arranging this. I've recorded this, hopefully recorded properly, and we can share it with Srikumar, and those who would like to see this presentation again, he will share it. Thanks everyone. Enjoy your evening. 73s. Goodbye.